Yeah, so welcome back, everyone. We're very happy to have Florent Krzakala again from ENS, giving the second lecture of his course on statistical physics and computation in high dimensions.
Thank you, Nike. All right. Thank you, everyone. Welcome here, or welcome back if you were here yesterday. I am assuming everyone can hear me well and you can see my slide. Right. Thanks. So let's proceed. Good. This is part 2. Yesterday we had something sort of statistical physics 101. That's a bit of a lie. You know, it was 1 hour, so there is only so much you can do. Still, it's time to move on. I will assume that now you are mastering all these techniques, and even though I went quickly on them, we are going to move to maybe a more interesting part, which is to talk about an image and a sort of phenomenology that was discussed a lot in the community of statistical physics, but also computer science, and that was the subject of intense activity over the last, let's say, 5-6 years. And I will review it, and that's about computational and statistical phase transition. Again, I remind you that we have additional materials, not an exercise that can be found on this address. There is this review we wrote with Lenka a few years ago. It's not entirely outdated yet. And also on the topic of today's lecture, I want to mention this amazing set of notes that you can find on arXiv by Afonso Bandera, Amelia Perry, and Alex Fine. It's really, really good, especially if you're not a physicist, maybe you will find this clearer. All right. So without further ado, let's go. Right, the question I want to discuss today is the following one. How hard is it to learn from data that have been generated from a probabilistic model? All right, so now the next is, the next 2, 3, 4, 5 minutes will maybe sound pedantic to my fellow panelists and for many of you. And it is certainly pedantic, but this is going on YouTube, it's registered, so I'm trying to think to reach a broader audience here. So I want to come back to very basic questions. So this is very good questions. We have data coming from some model, and we try to learn something from them. The parameter that generated the data, we try to learn something from this data. How hard is it? Okay, so I'm borrowing these slides from Andrea Montanari. I really like them, because they carry very well the idea. So here I'm caricaturing. It's really a caricature of situation, but it's often useful to do so. Well, the answer to those questions depend who you ask. Traditionally, if you are thinking about statistics, and certainly that's true in the very old days of Fisher and Shannon, and even before them, Laplace, well, it's easy, you design the probabilistic model for data, then you try to find the best optimizer, and you work it out. And in fact, there is a good theory, statistical theory, that tells you how to design good estimators for the quantity you are trying to learn. And often you can show that these estimators are asymptotically efficient. And with enough data, you can solve the problem, right? And in these days, we did not really care about modeling of computation, also because this was not really high dimensional problems. If the dimension is 3, well, exponential of 3 is not so big, so it's probably okay. All right, now that's information theory and stat. Of course, computational complexity theory in computer science grew up in a very different way. It was really about computational complexity classes, and at least at the beginning, of course, there was no modeling of the data. It was really a worst case analysis. You have this model of universal model of computation, and you ask yourself, is your problem is in P, and so on and so forth. There's a full hierarchy and so on and so forth. But there was no modeling of computation. So of course, this is not true anymore. There is a lot of activity in this branch here with trying to work, for instance, on adversarial problem and semi-adversarial, semi-random. There are a lot of activity. But let's leave us with the following. Data, in practice, are far from worst case, right? We should not expect them to be the worst case. And in fact, NP-hard problem is solved every day in practice. Think neural network, think optimization of coloring problem or that problem. So, it's probably interesting to ask you, what is going on here. And this is what I will discuss today in limited view and the one that emerged from this line of work. And more precisely, I will look at these two questions, right? So if you have probabilistic data model, how hard is it to learn something from them? If you have unlimited computation, so that's a really information theoretic way to learn. And how can you do if you have limited computational resource and let's say polynomial, low polynomial algorithm? All right, so a good example is the following one, clustering. So this is a very famous example. These are gene expression correlations. So these are genes in corn. It's actually in corn, and people are looking to the way these genes are expressing themselves in different cells. And you see that some genes express themselves together quite a lot, and then you can try to cluster, and this is how it looks. Okay, so clustering is a very, very hard problem. If you want to solve it, a priori, you have to try all the possible combination left and all the permutation of the genes. So it should be hard, but people do it in practice. So let's try to see if we can understand this. But of course, we're not going to see to look at something that hard. And what I will discuss today will be the following problem, right? So we have variables, so n variable, and let's say that some of them are correlated and some of them are not. Okay, in this example, we have 4 groups of variable, and I'm drawing an adjacency matrix or graph if you want. But essentially, variables are correlated. Well, there is a point. Variables are not correlated. So this one and this one, well, it's white, right? And this is a model in which we have 4 groups of variables that are very much correlated together, while they are not correlated too much with other, at least less correlated with the other group. Okay. Now, of course, in reality, data are not given to you colored like this. You're given an adjacency matrix, so it's more like this, black and white. And it's worse, they are not given to you in order. And this is actually the same matrix. And well, the task of clustering is a task of identifying the permutation that will go from here to here. Right? And well, it doesn't look entirely easy. So let's dig deeper. So in fact, the example that I just showed you is an example of an instance of the stochastic block model. It's a very, very much studied problem. It's actually hard to track it down. I think it first appeared in '83 in this paper by Holland, Lasky, and Lennart, and that's the context of social networks. And it appeared in computer science in this very nice paper by Dion Friese in '89. They called it the planted something model. And they introduced it precisely for the same kind of question I'm asking here. How hard is it to find a hidden solution here? All right, so here is the model. More formally, we have n variable. Each has assigned one of the Q group or Q colors. It's easier to think about colors. So the Ti's can take value from 1 to Q, and I is going from 1 to n. And the way you work is that once you have these colors or these groups, this assignment, you generate an adjacency matrix according, well, to these probability rules. You put a link between I and J with probability P, Ti, Tj. So this is depending on their colors. And the model is set up by this probability matrix, which is giving you the probability that there is a link between group 1 and group 1, between group 1 and Q, and so on and so forth. So actually, it will be convenient not to work with this matrix, but instead with this rescaled one, right? I just divide 1 over n times c. So if you want, c is just p times n. And I will work with this matrix instead. Now, once you write this, the average degree of your graph, because of course an adjacency matrix like this one can be seen as a graph, is given by this formula, okay? Now, the goal is, I'm giving you the adjacency matrix, I'm giving you the graph, and you are supposed to find back the underlying partition into groups. All right, so please try to remember this notation for what follows. Eta is the probability that each variable go into one group. We are going to focus on the symmetric stochastic block model, where we have an equiprobability. So a priori, each node can be one of the Q group with equal probability, one of the Q. Same for the matrix. We are going to take a very simple case. We take a diagonal here, P in, and everything out of the diagonal is P out. That means that we have a probability to be connected with variable in the same group, P in, or C in divided by N, and a probability to be connected with everyone else, which is P out, or P outside, or if you want, C out divided by N. In that case, the average degree is just D equal 1 over Q, C in plus Q minus 1, C out. Okay, so this is the model I'm going to focus in the rest. All right, so let's start. Well, let's start with the information theoretic answer. We have such a problem. How hard is it to find back the hidden assignment? Well, in theory, it's not hard at all. We know precisely what is the best thing to do. In fact, if you want, for instance, to minimize the mean square error for your estimator, the best thing to do is just to sample assignment from the posterior measure, which is written here. So the posterior measure, of the assignment, possible assignment Ti, given the graph, is given by this simple formula. Well, that's simple formula. This simple exercise to show it. So here is what you are supposed to do. Well, you ask a sampling machine to output many configurations from this posterior, and then you compute averages. That is what we do here. So we count how many times, the variable 1 is in color 1, how many times variable 2 is in color 2. We marginalize, we just take the average, and that's it. This is a base estimator, and it should give us the minimal mean square error. And the base overlap is also obtained in the same way. You just look at each of the variables and you pick up the color in which it is more often. Okay, so it's easy to do, except we have to sample from this measure, which of course is not easy. But let's try to do it first. Here I have done it. I wrote a Monte-Carlo Markov chain for you. I ran it extremely long time. I use my best computer. I'm pretty sure that I'm mixing. So these are, I'm confident I'm extracting a good configuration from this sampling problem. And then what I'm showing you is the overlap, that is the normalized fraction of correct level that I find with this procedure for different graphs indexed by C out divided by C in. Okay, so when epsilon is large, well, it means that C out is large, so there is more probability to be connected with people outside than inside your group. Of course, if C in is large, epsilon is small, and then you have this very well-defined cluster, so it should be easier. And in fact, it is easier. We see that the overlap I find, which should be the best overlap, is very large when epsilon is small, and then it decay seems to go close to 0. And then in fact, it goes to 0 around here. Already, this is a hinting at the presence of a phase transition. All right, so what do we really want to know here? What are the challenging? Well, we would like analytically to get the asymptotic error. We would love to have an analytic formula that gives us this line when the number of variables is going to infinity. Of course, we would also be interested into devising a polynomial estimator because, well, MCMC is maybe not the best thing to do, and it's not always fast. Of course, this is hard because this is precisely the kind of problem we're interested in this event. It's a 9-dimensional non-convex problem. So it's not easy. And it's outside of the box of old-fashioned statistical learning theories because we don't have statistical consistency. This is really one of these high-dimensional problems where things are not easy. Now, of course, given the title of this series and given yesterday's lecture, you might not be surprised that there is maybe one good way to solve this problem and to give a solution, which is to use what we learned in lecture 1, the approach given by statistical physics. And in fact, indeed, statistical physics provides us tools to answer precisely these questions with the replica method we saw yesterday and its little sister, the cavity method. So this is a problem we looked a lot with Aurélien Dessel, Chris Moore, and Lenka a few years ago, and later with Thibault Lutzler. And in this series of papers, we tried to work out the solution to the question I just asked to you. What did we find? All right, here is what we found. First of all, everything depends on your degree. If you have a large average degree, things are slightly simpler. So if the degree is larger than log n, well, we can actually compute the replica solution. And it's very close to what we did yesterday. The replica solution is, as you saw yesterday, expressed in terms of a function, the replica function or the replica potential that you have to maximize. Here it is. So you see it's a function that takes into input m and lambda. M is a semi-definite Q by Q matrix, and you will have to maximize over this matrix. So yesterday we maximized over scalar, but here we have a matrix to maximize over. And we have this lambda that appears here. And lambda is actually the signal to noise ratio. It's given by this formula that you see here. And it seems that everything depends only on C in minus C out squared divided by D, the average degree. All right, so here it is. Once we solve this problem, this maximization problem, then the replica, which is a heuristic method, you saw yesterday how it works, tells you that the mutual information between the graph and the hidden assignment is given by this formula, lambda over 4 minus, well, the value of this function evaluated at its max. But the mean square error, sorry, the mean square error is given by the trace, or 1 over q minus m star. And the best overlap is also given by a function which is slightly complicated, so I didn't write it. But it's, again, a function of m star. Good. And what about the case where the average degree is not large? Well, in that case, we have to work a bit harder. In that case, we used actually the cavity method, but we have a very similar result. We have a fixed point equation to solve again and to extremize. It's just that, well, it's certainly a bit uglier. Now, the order parameter is no more a Q by Q matrix. Instead, we have Q distribution on RQ that maximizes cavity potential. Okay, so I'm just showing the formula here. It's a functional now. So you have to extremize this functional over this set of functions. It's, of course, a bit harder to do numerically, but if you work hard enough, you can do it. Otherwise, it's exactly the same. Once you maximize it, extremize it, actually, well, you can compute the mutual information with the exact same formula. And again, the minimal mean square error or the best overlap are given by formulas that are directly a function of the fixed point distributions that extremize the cavity formula. All right, so this is what is obtained with physics style method. You saw yesterday how they work in a nutshell. Now, after we did this work, there was quite a lineup of mathematical work that followed this prediction and expanded them quite a bit, actually. And we tried to prove many of these results and to build on them and to go beyond them. So the dense case is actually pretty much under control. Everything is rigorous now. There have been really long series of work. So I'm not going to read them. You will see here many of the people interested on this problem and who are participating at this conference. So actually this paper here and this paper here were written in Berkeley during my last visit. So this is nice. In fact, many of these works are using the Guerra interpolation I showed you yesterday. Now the sparse case is a bit more tricky. Okay, and maybe it's a more interesting case because it's, if you like community detection, it's really maybe closer to what you get in practical applications. It turns out at least the disassortative case when C out is larger than C in has been proven. And this is a nice work we did with Amin Kojaoglan and Will Perkins. And when I say we did, they did the really hard part. So it's a very nice work. And we actually prove that the free energy is correct here. It turns out there is no such proof yet for the assortative case, which is too bad because this is the one we really care about. And there are basically no work that tells you the cavity formula is correct in the assortative case. So it's still open. In fact, one of the reasons this is so is because we don't have a working interpolation scheme in that case. Anyway,
sorry, can I interrupt about that? So there was a recent, about a month ago, Amin and a bunch of co-authors uploaded a new archive paper. Are you aware of this one? I think it claims to do the assortative case as well.
But of course not. I should check it. Thank you.
Okay, I consider. I haven't read it carefully, so I'm not sure. But it's 80
we'll look it up.
As usual.
It's great if they will make progresses on this. Thank you. Can you send the reference in the chat?
Yeah, I'll put it in the chat.
All right, great. So we see that this thing start to crack. But anyway, even before proving the value of the free energy, many of the results that we discussed have been proven and expanded upon. And in fact, well, Joe himself has made an amazing contribution. And the location of the phase transition that we are going to discuss are entirely rigorous in particular. And for those of you who are interested, for instance, you can check out the nice review of Emmanuel Abbé on the topic. All right, so enough reviews. Let's see what actually this solution tells you. For instance, what we get from Monte-Carlo, and here is what we get from the cavity method. So we see it works perfectly well. And we have this nice phase transition here that for two colors at given value, the best overlap that we can get, even with infinite computational power, is 0. In other words, this means that if epsilon is larger than the critical value, which is here, asymptotically inference is impossible. Even the best estimator do not correlate with the hidden assignment. So that was a very interesting phenomenon. In fact, you can actually show that the kind of graph you create in this region are contiguous with Erdős-Rényi. All right, so I will not go into the definition of contiguity, but essentially it means it's really hard to distinguish them with Erdős-Rényi. In fact, there is no estimator that can make the distinction with probability 1. So when does this happen? Well, essentially, it happens when the lambda SNR is larger than something you can compute, which is order Q of Q. Okay, so it's the SNR, the critical SNR gets larger if you have more and more community. All right, so there is this phase transition, this information theoretic phase transition. If you have a large enough SNR, it's fine. You can learn something. If the SNR is too small, well, there is no way you are going to learn anything from your graph. Good, so we have answered this question. What about the second one? How are we going to do this in practice? Because of course, well, I was merely discussing infinitely long Monte-Carlo Markov chain, and we cannot do this in practice. So that was what was the question that motivated Dyer and Friesen in '89. And there have been a long series of work who try to get better result and to find algorithm that in polynomial time can output a guess that is better at the random guess, which has a finite correlation with the hidden truth. So you see here that as time goes by, we get better and better algorithm, and we start to have seed minus C out that is getting smaller and smaller. But we are not quite yet at the value that is predicted by the information theoretic threshold. So let's see what we can do. So again, as I said yesterday, physicists really love iterative algorithm, and in particular for problems like this, they are really in love with belief propagation, probably because one of the early instances of belief propagation was written by Bethe and Peierls already in the 20s. And if you take the initial of Bethe and Peierls, it's BP, like belief propagation. So it really means that we really love it. We can use these two words, and we are acknowledging two of the best physicists of all time. All right, so why do we like BP? Because BP is exact on graph, which are tree. These graphs are not tree, but they are tree-like. If you zoom close enough, it's very easy to see that any finite distance, if you have a large graph coming from the stochastic block model, you will not have loop. So we kind of hope that something like belief propagation will be really, really good. In fact, the whole theory of statistical physics of this problem is built around the idea that you can decompose the Gibbs measure into a fixed point of BP. So it's really natural to run something like belief propagation. All right, so how do you write belief propagation for this problem? Well, this is it. It's written in terms of this thing called messages. So the messages from I from K to I here, or from I to J, what it really means, it is the estimation of the marginals for the colors and the assignment of this nodes if J was not here, right? And this one, K to I, is the assignment, it's the marginals of K if I was not here. Now, it's very easy to write a recursion on trees, telling you what these marginals should be given these, and what this one should be given these two, and so on and so forth. And this is the formula. So basically take these two marginal here and compute this one, and so on and so forth. Okay. So BP runs in linear time, at least that's true on a tree. On a graph, you have to make it converge. It's not always easy. It's not actually guaranteed to converge, but if you dump it enough, it apparently does so. And so it's really a polynomial algorithm, right? Actually linear in N. There is this bad Q square that can get a bit nasty. We have an implementation here if you want to run it. All right, so what happens if you run BP for this problem? Well, this is what you get. You get something which is basically not distinguishable from Monte-Carlo itself. Okay, this is what we get with BP, and this is what you get with Monte-Carlo for a graph of degree 3 and 2 groups. This is for 4 groups in the graph of degree 16. So, you know, we get something amazing. So that's great. It seems that BP is solving all our problems. It performs optimal estimation in polytime. Problem solved. And now we can just move to another problem. Well, not quite. Because of course, you know, if you make experiment, then you really realize that BP sometimes fails. And when it fails, it doesn't just fail, it fails spectacularly. Like it doesn't beat a random guess. So there is here one such example. It's an example which is a disassortative case. So every community is not connected with people in its own group. It's a planted coloring if you want, with 5 colors, and it's a very large graph, 100,000 nodes. And here I'm changing the average degree. Now the optimal overlap we should get, information theoretically, is this one, 0, but it jumped spectacularly here. I'll give you that. And if we run BP instead, well, here we don't find anything better on a random guess until we reach 16, where boom, magically we start to get the optimal solution again. So with this whole region where BP entirely failed. Of course, once you find it, well, you start to worry a bit. You check a bit what is going on with different cases, and you realize that BP actually fails quite often. These are other examples. This is the dense case. So here I'm plotting the mean square error. And this is for 10 color, 15 color, 20 color. And here I'm writing BP, but for those who know, this is more AMP, which is a dense version of BP, approximate message passing. So when you increase the noise or the inverse SNR, what happens is that, well, you go from 0 error to a finite error. And at some point, you get what you have here, which is what you will get by a random guess. Okay? So the line here is what we should get information theoretically. Here, note that I'm not plotting 1 over SNR, but Q square over SNR. Why? Because if you run BP, in this region, actually BP, which are just the dots and the crosses and the stars, is giving you the exact same MSE that you would expect from the optimal solution. So it's work. But once you reach Q squared divided by lambda, SNR, boom, BP is not better at a random guess. So it seems that something is going on around this value. So SNR, when Q squared divided by lambda is 1. All right, so I remind you that lambda SNR is just C minus C out squared divided by D. So what we find empirically is that BP seems to work if and only if lambda, that is C minus C out squared divided by D, is larger than Q squared. All right, can we understand that? Okay, one way to understand it is to realize that when BP fail, its marginal are basically 1 over Q everywhere for each color. So maybe a good way to work is to say, well, BP is a bit too complicated. So instead, let's linearize BP around the trivial fixed point and see what happens to the small perturbations. So we write all messages as 1 over Q plus epsilon, and epsilon is the small messages, and then we can linearize the belief propagation recursion. Well, if you do so, this is what you obtain. This set of epsilons obey a very, very simple recursion. In fact, it's just a linear recursion, perhaps not surprisingly, where B is an operator. It's a Dn times Dn matrices. So it's a matrix that is twice the number of edges times twice the number of edges, which tells you how directed edges are connected on the graph. Because of course, this is what matters for BP, right? Once to optimize this message, I need to remember that I take this message and this message. And so this matrix is just the adjacency matrix that tells you which directed edges are connected. Okay, by the way, it's not a symmetric matrix. All right, so now we have a much simpler object. It's all linear, and so perhaps we can try to understand what is going on. So this idea was actually proposed by a group of authors, myself, Christopher Moore, Elkanan Mossel, Joe, Alan, Lenka, and Panzang in 2013. And our idea was, well, if we look at this matrix, probably, they should converge to the eigenvectors of this matrix. So maybe we just can forget about all this BP nonsense and just look at this matrix, and that will give us an algorithm, right? So it's spectral clustering algorithm. Except that instead of looking to the adjacency matrix, we would like to look to this matrix, which is called the non-backtracking operator. Okay, it's called non-backtracking because it describes non-backtracking walks over the graph. These two directed edges are connected with this one, but this one is not connected with this edges. So the kind of walk you do here cannot go back, right? They are non-backtracking. That's the difference between the adjacency operator. So if you want to check this idea, what you have to do is to work out the spectrum of the matrix and the property of the eigenvectors. This is a bit harder than the usual matrices, largely because it's not a symmetric matrix, but it turns out it's a good idea. So for instance, this is what happens when lambda is smaller than the q squared. You have only one value out of a circle here. By the way, there is a circle because the eigenvalues of this matrix are complex. And they are all in the circle of square root of d, except one, which is actually entirely trivial. Okay, it's not correlated with hidden signal. And what happens when you cross q squared, when the SNR is large enough? Well, you have an additional eigenvalue that comes out, and you can show, this is what we did in this paper, and later on that was proven in this series of work by Massoulier, Bordenave, Lelarge, and then Abbé and Sandon, who generalized it to more than two communities. Well, you can show that the eigenvectors connected to this eigenvalue is actually correlated with the ground truth. All right, so that's nice because looking at the non-backtracking operator allows us to understand what's going on with BP. And once you know this, you can also forget BP altogether and just work with the spectral method. So this is the kind of overlap you get when you look at the eigenvector associated with this guy. You see you have good correlation with those guys, which are color 1, and those were color 2. All right, now we have been able to make progress. We have this matrix. We can actually provably work that it's working better than random, at least when lambda is larger than q squared. Now we understand why BP works when lambda is larger than q squared. It's because BP is basically starting, it's the first step when its message starts to be a bit different from 1 over q, it's following the non-backtracking operator. So of course, if this doesn't work, it will never work. And it has a lot of interest in itself, actually. It's improved drastically over standard spectral method, and there are many other applications for this thing that goes beyond what I'm discussing today, and that will be the subject of another story. But at least now we understand what is going on. All right, so let's summarize. Well, everything is dependent on the SNR. If the SNR is large enough, larger than q log q, then it's possible to do something. Before, no way you can learn something from your graph. Now we have this region between q log q and q squared where we don't know how to solve the problem. And certainly belief propagation and non-backtracking do not work. And finally, when the SNR is large enough, larger than q squared, we have this algorithm that works perfectly well, and we are all happy. Good. So this is an example of an impossible hard easy pattern. Here we have a statistical transition where it becomes statistically possible to make a learning, but the computational transition, when it becomes only possible in practice, is here. And we have a statistical to computational gap. Well, of course, you may say, well, that's not quite a convincing story, because I just told you that BP doesn't work here, but maybe you don't agree with me that this is a good algorithm and you can try other things. In fact, what about other algorithmic approach? Maybe it's possible to have a good algorithm that is efficient and that works perfectly well in this region. So we tried. There have been many attempts to beat this Q-squared threshold, to find a polynomial algorithm that gives you provably, or even empirically, a positive overlap with the truth for lambda smaller than Q-squared. Of course, Monte-Carlo simulation fail. You realize that if you run Monte-Carlo starting from a random initial condition at random, well, it seems that you have to run it exponential time to start to see something good. So it's not good. Well, if you go to the computer science department, people will start to work with the sum of square hierarchy, and there have been a long line of work on this problem, including many of the people attending the conference. And it failed exactly at the same point, at Q-squared. So that's very interesting. It seems to say that really there is something deep around this moment. People try to use neural nets, everything. Everyone is trying to learn neural net this day, and they say, let's ask a neural net to learn the best method. Well, if you try graph neural network to invert this problem, to find the assignment in stochastic block model, it fails to beat the Q-squared threshold. In fact, it's interesting. This method seems to just relearn the non-backtracking matrix, which maybe is interesting because it means we were maybe not so clever when we designed it, or maybe we were very clever because you need a huge amount of computational time to do it, while we did it just talking between friends. We tried even quantum annealing at some point. Even we don't have a quantum computer, well, we have quantum replica method and quantum cavity method. So we try to see what's going on, and we show that it doesn't work even if you have a quantum computer. So we don't know anything so far that worked in polytime in our version. We don't know of any method that actually is able to output something that correlates with the truth in this region. So, at this point, we feel obliged to make a bold conjecture. Maybe this is hard for all polytime algorithms. Maybe not. And what will be very interesting is to have a very clear-cut definition of a set of algorithms that will not work here.
Hey, Florent, this is
Yes.
Sam. Can I just make a clarification that I don't think we can actually prove this particular sum of squares lower bound yet. We have some reasonable evidence for it, but it would be a really great open problem.
Good point. So that's, we need to add this one in the list of problems that Nike and Celil are asking.
Yes, thanks.
Good. Well, anyway, proving that it stopped here is one thing. What will be even better is to beat it. It will be amazing to find something that goes here. Now, that was all about community detection, and maybe you say, who cares about this problem? But the point is, this seems to happen all the time. In most of the problems that we are devising and trying to study, we find something like this. This is a variant that people like a lot, called the planted clique problem. Here, what you try to find is a set of fully connected variable here, a clique inside a random graph. Here, it's a random graph. It's a GNP with p equal 1/2. So the probability to be connected with someone else is 1/2, except for a clique of size k. Okay. Of course, here the clique is easy to find, but this is a perturbed, the permuted graph, and you don't find it so easily. Now, as far as we know, it's impossible to find the clique if the size of the clique is smaller than something which is of order log n, because naturally cliques of order log n occurred in GNP 1/2. Now, people have been trying hard to find good algorithm, and they all seems to, at least for clique polynomial time, it seems to stop to fail around the square root of n. So here we don't know of any algorithm, and here we have very myriad of algorithms that work here. Now I want, to give a last example because it's interesting and it is connecting to the lecture of yesterday, which is a balanced asymmetric communities case. Okay, so it's community detection with two community of densely connected groups, but one is small and the other one is large. Okay, so there is a size rho n and 1 minus rho n. And to make the problem difficult, we are forcing the graph to be a regular graph with a fixed connectivity. So every point has the same connectivity and its neighbors. So that makes it very hard to distinguish between the big group and the small group by just looking at their local connectivity. If you do this, here is a phase diagram. It's very interesting. So here we have rho. So 1/2 is just community detection with two groups. When rho is going to 0, well, you start to have a huge group and an infinitely small one, and everything in between is here. Now, everything seems to depend only on this parameter delta, which is an effective noise, or inverse SNR if you want, which is P, 1 minus P. So P, I remind you, was the fixed connectivity of average connectivity of the graph was Pn. And what is going on is the following. When the noise is too large, well, we have this phase here where it is impossible to learn. When the noise is small or its SNR is large, it's very easy to learn something correlated. In fact, the spectral algorithm would work. And since this is a dense graph, you don't even need the backtracking matrix. You can just take the adjacency matrix and you have this thing called the BBP transition that will work. Interestingly, you have this region here, which is a hard region here. So here we know that it is statistically possible to return a good guess, but we don't know of any algorithm that work. Okay, and certainly belief propagation doesn't work. Now I want to make the connection with what I told you yesterday. So the nice thing is that for this dense graph, the free energy can be written in a very short way. This is it. Actually, this is not the free energy; it's the mutual information. This is the same, except that you have to minimize it. So this is the replica mutual information. It's a formula that depends on the scalar m, and its minimum is the actual mutual information. This is proven. So depending on the value of the noise, this function, this replica potential, look like that, or like that. And the minimum is changing. So here it's very small noise. The minimum is here. This is error, it's small. When we increase the noise, well, the minimum is going to position where the error is a bit larger. And suddenly, when you go from here to here, you have these two minima, boom, and this guy becomes a minima, and the error deteriorates fast. And when the noise increases again, well, at this point, the error is really bad. Right, so the interesting thing is that you can just see this from looking at the replica free energy. You can actually see its minimum changing. Now, why am I speaking about this problem? Well, because in that case, belief propagation can be written in a very much simpler way, which is called approximate message passing. And it's just an iterative algorithm, which you already saw yesterday, okay? And I will not go into detail, but the important thing about approximate message passing is that, as we discussed yesterday, it's an algorithm that really just trying to find the fixed point of the replica potential. So if you ask, what is the overlap between the estimation given by IMP and the truth, and you call this M of T, well, the overlap is following at each time this expression, which is just the fixed point expression, is trying to climb, it's trying to find the fixed point of the replica potential. Now, why is this interesting? It's interesting because you can understand and you can read off the behavior of IMP just by looking at the function. Now, if the function looked like that, so yesterday I was trying to climb the replica potential, but today it's the replica mutual information, which is just a constant minus it. So I'm trying to descend it. So I'm trying to minimize it. If it looks like that, well, it's easy. An algorithm will probably do something like this and stop here. So that kind of potential is good for IMP, and IMP actually achieves MMSE. Now, if the potential look like that instead, when you start for large error, well, you iterate and you will get stuck here. So when the replica potential look like this and develop a secondary minima, well, often it means that your algorithm will have problems. And in fact, this is how we can read off the behavior of IMP and belief propagation directly from the potential. It's very practical. In that case, we don't achieve MMSE. Here we achieve it because, of course, this bad minima is still here, but now the bad minima is actually the best one we can do, so it's fine. Okay, so that kind of situation where the replica potential has two bumps and develop local minima and maxima is where we are expecting trouble. All right. Now, these were just examples of the stochastic block model and the planted clique, but of course, the last 10, 15 years, we have found pretty much the same behavior almost everywhere. And it's SBM and plotted clique. We found it in generalized linear model, in some sample model of neural network, in dense platted symmetrics, in planted constraint satisfaction. People knew about these in LDPC error correction. They know that BP doesn't achieve capacity. It's the same in sparse PCI, Gaussian mixture clustering, and so on and so on and so forth. In fact, the list goes on. And Lenka will speak about this again for 2 more lectures, so I will not spoil it too much. And we had a very nice workshop organized by Sam, Andrea, and David 2 years ago about this topic in Stock. All right, my time is almost up, but this is pretty much what I wanted to tell you, which are what are the consequences of the formalism we saw yesterday, and where do we stand now? Now, before giving up the floor, I want to make 2 final remarks. First one is about the physics intuition. Why is it so? Why is it that the fact that the potential has has developed this nasty bad local minima, how does it have to do with the fact that everything seems to fail? And the short answer is I don't know, but let's try to see if we can give a physics intuition. Now, physicists are really, really used to this potential and their maximization. In fact, our whole understanding of condensed matter theory and phase transition in the world is based about this. We look at these, we compute these for materials, and nature is just like us here. Nature is trying to minimize free energy or to maximize entropy. And so you have this function, and it moves locally, and it's trying to do something. Now, if you study your phase transition, you will know, for instance, that diamond is not the true minimum of the free energy, or it's not the maximum of the local entropy. Actually, diamond is a local maxima. Nature tries hard to find the ground state of a set of carbons, and it's stuck in this diamond case. But if you will give it exponential time, and you wait 1 or 2, twice the time since the Big Bang, well, eventually it will reach this point, and the true equilibrium will be graphite, powder. So diamond is not eternal, actually. It's eternal in practice, but not statistically, if you want. So we are used to this. We call this first order transition, and we know that there is basically nothing much you can do in this case. So it's very tempting to think that, well, that's it, we have a nice intuition. There is a hard phase because there is a barrier in the free energy potential constraint at the distance from the solution. Right? You remember I introduced this idea yesterday of the constraint free energy. Right? And that's it. We go here and we never go there. And it's very tempting. And in fact, there is a lot of interesting activity in mathematics that use this. For instance, you can prove that if you are here and if you try to make sampling with local Monte-Carlo algorithm, it will take exponential time to go here. It's actually one of the ways you prove this thing in mathematical physics. So maybe if it's hard to sample starting from here, it's no wonder that it's hard to find this thing. And we really loved this idea. And with Chris Moore, we thought a lot about it. Then I remember with Ahmed, we spent a lot of time trying to prove that this is actually what is going on. And one of the reasons that this is tempting to use this is that we have this relation that I told you yesterday, right? The replica symmetric potential is an upper bound on the constraint free energy with equality at the max, right? So this is how the free energy looks from the replica point of view. And of course, it's good at the max. We proved this. All right. So is it true? Is it true that secondary minima appears at the same value of the SNR in the 2 functions? Because these are not the same function. Remember that IMP is not claiming the constraint free energy. IMP and BP are claiming the replica symmetric one. So they stop to work when you have this minima or maxima appearing in the replica symmetric function. So maybe this maxima appear at the same time in the replica symmetric function, and it's a true constraint-free energy. Well, it turns out that this is not true. So I believed this, and it's just plain wrong. So this explanation is wrong. This is not true. In fact, that was shown in a very nice work last year by Lenka with Fabrizio Antenucci, Silvio Frantz, and Pier Francesco Urbani. Such situation exists where the replica symmetric free energy is nice, has only one maxima here, while the true free energy, constrained to a distance m, has this local maxima. That means the following, and I'm really puzzled by this. If you increase the noise or decrease SNR, and you ask yourself, well, when does the local maxima appear in the true constraint free energy? Well, it happens somewhere. When does it appear in the replica symmetric free energy? It happens later. Now, the point is that message passing work in this whole region. So thinking that when the true function develop a local maxima is the moment where you have a real problem for finding a statistical solution is entirely wrong. And I was surprised by this, but this seems to be true. What seems to matter is not the true constraint-free energy, but the replica symmetric one. And that seems to say that there is something really fundamental about AMP and BP, which is a line of thought which is pushed, for instance, by Andrea Montanari and in his group. In fact, he was able to show that in some limited class of algorithm, AMP is the best. But still, I'm not really satisfied with what is going on here, and I find this very interesting. All right, a second remark that will be short, I hope, is: does this always work? When I do BP and AMP, does for any problem I can really run them? Is it true that they always give me the true threshold for hardness? Of course not. We need to be sure that AMP and BP are the right tool for the job. And how do we do this? Well, first of all, and this is to answer a question from Nike, I believe yesterday, scaling matters. Okay, no, that was Celil who asked me this. We need to use AMP, TAP, BP, and replica in cases when it makes sense. And for instance, we want the free energy to have a correct limit. When you take the limit of the free energy at n going to infinity, is to have a finite limit. Why? Because, and by the way, you remember that in lecture 1, I carefully designed my cost function with an n here so that the limit exists. And I think Sam asked me once, why do we have this np minus 1 somewhere? I have to do this if I want to be able to make this computation. Now, why is it fundamental? Because the whole credo, the whole belief of physicists is that what you do here is decompose the Boltzmann measure into many fixed points of TAP, AMP, BP, or whatever. But these message passing algorithm, their fixed points correspond to a probability measure. And if you find all of them, you have the full probability measure. This is really what all the physics methods are using. This is really the important thing. Now, that means that the fixed point of this algorithm should be correct. And that happens only if you are scaling things properly, asymptotically. By the way, this is not some physics mumbo jumbo. You can actually prove this. There is this nice paper by Emile Koja-Oglan and Will Perkins who actually show that you can decompose the Gibbs measure in well-scaled problem on random graphs into collection of measures that correspond to fixed point of BP. And you can do the same on fully connected problems, and that's due to Antonio and Okosh. So we need to have this fixed point of AMP and TAP and BP to make sense. Now, one case where they don't make sense is tensor spike model. Okay, so the way we set up the problem is as follows. Consider the following tensor. So we have x0, it's a vector in n dimension. Now we take its tensor product. Okay, so now it's order P tensor of rank 1. And I'm multiplying by, well, this term do not matter, but certainly I'm divided by n to the power p minus 1 over 2. And this is really due to this nice limit in the physics sense. Now, this is a order p rank 1 tensor, but I'm not giving you this one. I'm giving you a noisy version where I'm polluting every component of the tensor by a random Gaussian IID noise with variance delta. Now, what is going on? Well, if you try from the tensor to find back the vector, well, you can try to apply all our tools. And here is the main theorem that we have. There is a replica free energy that you have to maximize, blah, 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 blah. And again, the maximizer is giving you the minimal mean square error, okay? So it's the same story all over again. You can write message passing. This is how it looks. It has been written in that case by Andrea Montanari and Emile Richard. And you have a state evolution, so you can also track what the message passing does. Same story all over again. So what is going on? Well, in a nutshell, this is what is going on for this problem. When the SNR is increased, or when the noise is reduced, you go from an impossible phase where it's impossible to find the spike to a phase where it's possible statistically, if you have infinite computational power, to find the spike. And we can compute exactly at which value of delta or 1 over delta this is going on. It depends only on the rank of your hidden tensor. And these are the values that you find. Now, what is perhaps more interesting is that if you try to run IMP for this problem, and that was discussed by Emile Richard and Andrea Montanari, you see that it's really, really not working quite well. In fact, you have to go really on the right of this picture here to go to, SNR, which are of order n to the p minus 2. At this value of the SNR, all the approximation you do in statistical physics don't make sense at all. So there is no reason to think that IMP is really doing the job, at least from the physics point of view. Now, fine, maybe that means that this is hard here and easy here, but we know of better algorithm. And in fact, we know that working with SDP and also with tensor unfolding, we have algorithm that works way before IMP. All right. Again, this is perhaps not so surprising. IMP is no reason to be really good here, because the statistical physics approach, which tells you, well, we need to work and decompose into states that are fixed point that will behave well, doesn't make sense. Now, why? Because belief propagation is only the first step of a full hierarchy of approximation. You start with mean field, then you have BP, and then you have much things. It turns out that in all the problems we are looking at in general, this approximation, this hierarchy stop after BP. So you stop at order 2 and BP is fine. Once you go out of BP comfort zone, well, BP doesn't work anymore and you have to take more and more terms. And this is called the Kikuchi hierarchy in physics. There is something equivalent called the Plewka hierarchy. And that was discussed in this very nice paper by Ryoki Kikuchi in 51s in the physics literature. So for well-scale problems, the hierarchy stops at BP. For this hard problem, it doesn't. So there is no reason that we would believe that BP works. So my belief was that there was no way to use Kikuchi hierarchy because it was too hard. It turns out I was wrong, but I will not go into detail. If you want to know more about how to redeem the statistical physics approach and unleash the full power of the Kikuchi hierarchy, well, there is conveniently enough a talk by Ahmed that will be Thursday at 1 p.m. And he will go and discuss his amazing work with Alex and Chris using this approach, right? All right, I think I'm really hitting my limit of time. So I thank all of you for listening to me. I will leave the floor to Lenka. I told you what I wanted to tell you. Maybe a last point. I just moved to EPFL recently. I'm starting in 1 week. And we are starting a group here. If you want to work in this amazing place with that kind of amazing view, this is the Mont Blanc here. Well, write me a mail. We are looking for talented postdoc and students on these topics and also many others. And with this, thank you everyone for your attention.
Okay, thank you so much. Do we have any questions? So maybe I will start with a question. Actually, I think I missed the story about the constrained free energy, and Ahmed is also here. So I was hoping that the two of you could say a bit more about that.
I don't know, Ahmed, do you want to say something or should I?
Yeah, I can say something. So for the model that
let me put back the slide so that you know, it feels like that we are connected.
Sure.
This one is nice. Please.
Oh, you want this? Fine.
Yeah.
Yeah. So for the model that I worked out, which is the spiked matrix model, which is maybe a disordered version of the random Bayesian model that that Florent has showed. So you can do basically the same interpolation calculation, and so you can do it either for the full free energy or for a constrained free energy with a parameter m that you can choose, that you can just fix as a variable. And what happens is just really an algebraic trick. So basically, when you do the interpolation, then the error, that integral, the derivative that shows up along the interpolation path, when it's the full free energy, it's positive, so that you get a bound on the right direction. But if you constrain the free energy to have overlap m, then basically one of those terms that show up in the derivative will go away, because you just fixed the free, you basically killed it. You have a term that has an overlap minus m to the power 2. And since you've already constrained the overlap to be exactly m, then that term goes away. And it turns out that now the dominant terms are other terms that are not that one, and they turn out to have the negative, to have the opposite sign, so that you can have an inequality in the other direction. And so that's how you bridge the gap between the upper and lower bounds. So there is I can send the paper. We have a small note that explains this idea for the Spikes-Wigner model, and it's a very straightforward computation to do. But it's the main thing is it's really just an algebraic trick. Yeah. So
the constrained free energy, it's a system of two replicas that you have.
Yeah, right. So for the planted model, so you can have that, or for the planted model, you can just have a system with one replica combined with the spike, with the planted solution, and you constrain that overlap.
I see. And is the intuition that it should be the same as the unconstrained, but it's better concentrated, or?
No, so it has the same kind of concentration. It's just when you interpolate it, when you try to do the same Guerra interpolation, then the interpolation path has a different sign. So basically you go in a different direction. So because one of those terms that showed up in the interpolation will go away, and then the sign will flip magically. So there is a computation. It's difficult to explain on slide on like this on Zoom, but there's a computation that you have to do. Yeah.
Okay, thanks a lot. There's another question in the chat. So one of the someone asked, is there a physical interpretation of the replica symmetric potential? Yeah. I don't know, Florent, can you see the Q&A?
I'm looking at it. I'm not sure I understand the question. Sorry, is the Q&A on Zoom or?
Yeah, it's on Zoom. So the question is there a physical interpretation of the replica symmetric potential? I think as a function of m and whatever other parameters that you have.
Well, unfortunately, not a physical one, right? I mean, we like to think about the replica symmetric potential as this object, as a true potential with a fixed m, but this is wrong. You know, it's just a bound on it. So, you know, it's not clear what it actually means, this object. Now, there is an algorithmic interpretation of the replica symmetric potential. And that, in my opinion, is really the interesting thing about IMP. IMP, seen as an algorithm, is really just climbing the replica symmetric potential. And I think this is interesting because it gives us a relation between an iterative algorithm and the replica symmetric potential, which, you know, is surprising. That the algorithm is connected to the replica symmetric potential at value of m and not to the constrained potential. It's really connected to the replica one. And that is, you know, in my opinion, something interesting.
Florent, I have a question about this new finding that you said. So these two functions are not equal, but one can be concave and the other one can develop local minima. So that's quite surprising, right?
Yeah.
Like, so the one that you would expect is physically relevant is phi C, phi
yes,
superscript C.
I agree.
So what's going on there?
I have no idea. You know, I mean, I agree, right? Phi C is the true one. Is one. It's actually the true free energy, right? So you would expect that if you have a problem in the true free energy, you have a problem. But no, this is wrong. INP seems to be clever. INP is not attempting to climb the true free energy. INP is trying to climb the replica symmetric free energy. And there seems to be this case that the replica symmetric free energy is nice, while the real one is nasty. I was as surprised as you when I learned this from this paper. Now, the point is that people you can compute with replica theory the constraint free energy, but you have to use replica symmetry breaking. It's very interesting. My drawing is really bad here. Essentially, the replica symmetric. So if you compute the replica symmetric, if you compute with the replica method this object, this part is given by the replica symmetry, and all this region here, the non-convex region, requires some replica symmetry breaking. So it's kind of a complicated case, and that's essentially the kind of study that we're done here. Of course, heuristically with the replica method. But if I'm not mistaken, I think there are some papers by Dmitry Pachenko is trying how to, is actually proving how to compute this thing with replica symmetry breaking techniques. It's probably, doable to prove that this situation exists. By the way, that will be interesting to prove that this exists, right? Because it shows that there exists a situation where if you start at random and you do an algorithm which is not particularly clever, it's just a simple iterative algorithm, INP, you find something good. While if you start here, you run your Monte-Carlo will fail immediately. I mean, I found it really surprising. I was expecting, the kind of MCMC to work as good as INP, and it's not true, and I don't know why. It's certainly not intuitive. So by the way, this paper, I think they do this in a spike tensor model as well, if my memory serves.
There's someone has raised their hand.
Yeah. Okay. Thank you, Nick. Hi, Florent. Thank you for the talk. I just have a question related to going back to Nike's question on the constraint free energy. I guess I need to look at the paper that you have with Ahmed, but if I
I'm trying hard to see who's talking here, and I don't see anyone.
It's Christos. It's Christos Thembolidis.
Okay.
I don't have video somehow. Yeah. So.
Oh yes, I see this. Okay, but I see your name now. Good.
Yeah. So that is very interesting. That I need to look at your paper with Ahmed. But if I understand correctly, then the constraint free energy is always a lower bound to the replica symmetric energy. Is this true?
Well, you have to. There's
so
a problem, but sometimes I work with log z and sometimes minus log z. But
okay,
let's say that
I see. Right. Okay. So it gives one side. But let me ask you that. So my understanding is that
I think that this is always true, that the replica solution, whatever even the 1 RSB, 2 RSB, 3 RSB, 4 RSB, and so on and so forth, will be larger than the true one. In fact, the way we compute things is to take this function and break the symmetry until it stops moving. Then proving it in full generality is another story, of course. But I think this is always true. That the replica potential is a bound on the constraint potential. Yes.
I see. So this is not proven. But do you have some intuition of when it fails? So when replica symmetry is not true, what would fail in the proof that you have, for example, for the Wigner case on trying to show
very
that,
good. That is very easy. So, okay, the proof I use. So, that is a bit annoying because, of course, the cases I presented yesterday were entirely trivial. It's harder. But anyway, so at some point when you do this interpolation, you have something like q or n minus sum of the variable divided by n. And this is squared inside a bracket. And you need to send this to 0. And the way you send this additional term to 0 is by proving they concentrate. Okay, these overlaps should concentrate, and if they concentrate, then you send them to 0, and then you say, fine, my Guerra interpolation is equal to the truth. Now, what is failing in the proof is precisely this. Replica symmetry breaking exactly means that these overlaps do not concentrate to a single value. So at this point, the proof stopped to work because actually you cannot prove it concentrate. So you have to make a different integration path, and you have to try to see, fine, maybe it will concentrate to a more complicated function, and then you can try to prove this, and so on and so forth. But really, what breaks down is this concentration. Replica symmetry making is all about overlaps, not concentrating to a single value.
Okay, thank you.
Are there other questions? Okay, if not, then thank you so much, Florent. And Lenka will continue the course tomorrow. We have a short coffee break now, and then we'll be back at in about 15 minutes for the next talk.